When considering the possibility of life beyond Earth, we look for three main ingredients. The first one is key elements such as carbon, hydrogen, oxygen, and sulfur. The second is a source of energy. And the third, and perhaps most important, is the existence of liquid water.
Water is a necessary solvent in all chemical reactions that have to do with life. Energy is required to drive these chemical reactions, and organic matter is the material from which all life that we know of is made.
Life as we know it requires liquid water. Scientists believe that life on Earth started in our oceans. Now, through our exploration of the solar system, we've realized that the moons around the giant planets have the right conditions, that there could be liquid water underneath their surfaces. So that really sort of expands our whole concept of where you could have a habitat, where we might find life.
Water is fairly common in the universe. We've seen traces of water in large molecular clouds between stars. We've seen traces of water in protoplanetary disks. We've also seen traces of water as water vapor in the atmospheres of giant planets around other stars. And we know that water is in the atmospheres and interiors of our solar system's giant planets. So we know that water is ubiquitous throughout the universe. As far as liquid water, that's a little less common. Earth is the only planet in the solar system where we see liquid water at our surface. Moons such as Enceladus and Europa may have liquid water beneath layers of ice.
We're really expanding our understanding of what makes a place habitable. Instead of just looking for an Earth-like terrestrial planet that's a very specific distance from its star, we're learning that there can be hidden habitats that are underneath icy layers, and they can be a lot further out from the sun.
So we believe icy moons in the solar system actually harbor kilometers-thick oceans underneath their icy surfaces. These icy moons and their subsurface oceans may be some of the best places to search for life elsewhere in our solar system.
Enceladus is one of Saturn's many moons, and it's a very small moon that people tend to kind of ignore because it's so small, about 500 kilometers in diameter. But decades ago, in the 1980s, from ground-based observing, we found out that the location of Enceladus relative to Saturn happened to coincide nicely with Saturn's E-ring. And so we were thinking that Enceladus had something to do with the E-ring particulates, the icy material, but we weren't sure. What we later find from Cassini was that we directly determined that there are indeed plumes jetting out of the south polar region from cracks in the south pole of Enceladus in the crust. And it's dominantly water-rich material, just jetting out into space. And so the way we saw it, Cassini happened to be located where Enceladus was backlit from the sun. And so you saw this curtain of beautiful, diffuse material jetting out of the south polar region. Quite breathtaking, actually. Even more, we were able to use the different complements of instruments on board Cassini to go after the chemical composition of the plumes. And that's where things got really interesting. So number one, that's because of liquid water. There's definitely a liquid water reservoir subsurface below the icy crust, but that is there. Number two, the chemical composition of the plumes told us that there's a lot of organics, things that make up amino acid and things on life that are very interesting. And number three, what we were really looking for is a source of energy. On Enceladus, photons from the sun aren't going to work because you can't penetrate the tens of kilometers of icy crust to get down to where the liquid water reservoir is. But what Enceladus does have is hydrothermal vents. It's very hot into liquid water. That has a lot of analogies with the ocean floor, where we have a form of releasing chemical energy via something called serpentinization. And so we think that Enceladus might have that potential to have an energy source being chemical, not sunlight. And so you put all that together, and Enceladus has all the ingredients, or most of what we need, for life. That makes it a very astrobiologically interesting object to study.
Europa is one of the largest moons of Jupiter, and we believe that Europa has a subsurface ocean tens to hundreds of kilometers thick. And so this ocean may be one of the best places to search for life in the solar system.
There's been 3 space missions that have provided evidence for Europa harboring liquid water. The first one is Voyager in the late 70s. The second one is the Galileo mission in the late 90s. And most recently, Hubble, which detected plume-like emission from hydrogen and oxygen, which is closely related to the existence of water beneath its surface.
These plumes may be directly ejected through cracks in the surface of the moon, and therefore what we're seeing in water vapor plumes is the actual ocean water from the subsurface of the moon.
As these plume particles are ejected to space, solar radiation is going to excite these water particles, creating vibrational modes. Now, these vibrational modes are signatures that can be detected at infrared wavelengths by the Keck Observatory. So we observed Europa on 17 days. What we found is that the majority of observations have no presence of water. However, on one of those days, we detected water. We detected H2O. In the past, Hubble provided indirect measurements of water by detecting hydrogen and oxygen. But now we have directly detected water for the first time.
Both the Webb telescope and the Europa Clipper mission will give us a much more detailed picture of the surface of Europa, its cracks and crevices, detailed pictures of the water vapor, as well as other molecules that may also be emanating from the subsurface of Europa. So both of these missions will give us a great picture of whether Europa is truly habitable.
Titan is a moon of Saturn. It's the second largest moon in the solar system, and it is about 2 times larger than Earth's moon and actually bigger than the planet Mercury. And Titan is also interesting. It's the only moon in our solar system with an atmosphere. It's surrounded by sort of an envelope of gaseous nitrogen, just like our own Earth is. Titan was first discovered by telescope observation back in the mid-1600s. The first spacecraft observations were made of Titan during flybys through the outer solar system. That was in the late 70s and in the 80s. But we really were able to explore Titan in depth with the Cassini-Huygens mission. The Huygens probe was dropped into the atmosphere of Titan, and it made measurements of chemistry, and it took images as it fell to the surface. And that was back in 2005. And since then, the Cassini orbiter made over 100 close flybys of Titan.
Cassini, in its design with the different instruments, we purposely were picking instruments that could go into longer wavelengths into the infrared so we could really understand the moon. We were able to basically peel back the layers of Titan to really see what was below, and it was remarkable, very Earth-like.
The landscape is similar to Earth's in many, many ways, but with a little bit of a twist. So on Titan, you can find dunes, you find lakes, there are river channels. The atmosphere is very dense, and you can get clouds and smog, and you even get rain.
We saw winds, we saw seasons, and one really important thing we saw was liquids pooling in the polar regions on the surface, a lot of it.
But because Titan is so cold, those features are all made of very exotic materials compared to what we would find on Earth. So the lakes and the rain are made of liquid methane. The crust that forms the surface of Titan is actually water ice, but it's so cold that it's as hard as rock. And in the atmosphere, we get this organic chemistry that forms large organic molecules and particulates. They fall down to the surface and then behave like dust or like sand does.
So it makes us want to go back to really understand the complex organic environment of that surface and what it means for either past life or maybe future life.
Dragonfly is a mission that was just selected by NASA to fly to Titan and arrive in the mid-2030s. Dragonfly is going to make a whole bunch of measurements to help us understand the environment on Titan and its potential for habitability. We'll be taking measurements of the atmosphere. That includes things like pressure, temperature, winds. We'll probe the surface to try to understand what materials the surface is made out of. We'll also be drilling into the surface to look for the types of organic molecules that are present and to try to see if we can find any examples of compounds that mimic the types of building blocks we know we need for life on Earth. We don't really know how life started on Earth. We don't exactly know what the chemical environment of Earth was like before life started. So with Titan, we have this really unique opportunity. There are times in Titan's past where there could be liquid water on the surface. Impact craters can generate impact melt, and there's a potential for possible cryovolcanism to erupt some liquid water onto the surface. And so we know that there's a rich organic chemistry going on in the atmosphere. We know that's depositing to the surface. If there were times where those organics and the liquid water environments were mixing, then there may be some really interesting chemistry taking place. When you have these processes operating for hundreds of millions of years, how far can they get you down that path of chemical complexity? And can we see reactions and molecules that start to look something like what we think of as essential elements for our biochemistry for life on Earth?
In the future, looking forward as opposed to looking back and thinking about Titan as a chemical laboratory for the prebiotic Earth, I like to look forward thinking about what's going to happen when the sun evolves and warms up and the habitable zone actually moves out to where Titan is. And it will. You have all the organics, you're going to have a source of energy. All we have to do is melt the frozen water and we're going to have a pool of organics just embedded in liquid. Titan might actually have a chance at that point to harbor life.
So when we think about ocean worlds, it's good to compare them to what we know about Earth. In total proportion, Earth is about 0.1% water. An ocean world is a body that has, in proportion, about 10 times more water than Earth does. And when we think of the TRAPPIST planets, those planets have about 50 times more water in proportion to what Earth does. Ocean worlds do appear to be common in our galaxy. As far back as the early 2000s, we had astronomers, some of them still here at NASA Goddard, that suggested that we would have ocean worlds orbiting low-mass stars. Recently, we've looked at about 52 exoplanets, and these are low-mass exoplanets. And what we found is, of these 52 planets, 1 out of every 4 may be an ocean planet. And when it comes to these ocean planets, over half of them may be ice-covered ocean worlds. And so Enceladus and Europa may serve as small-scale analogs of these planets.
So there are a number of different ways to search for life on planets around other stars. But the key method is the study of the atmospheres. We can search for signs of life, biosignatures we call them, things like oxygen, water vapor, carbon dioxide. Even more unusual biosignatures, things like chlorofluorocarbons or other things that are only produced by intelligent life. By looking for these key constituents of planetary atmospheres that signal life, we can discover life forms on other planets that we could never actually visit in our lifetime. So this is very analogous to how we study the atmospheres of moons and planets in our own solar system, and really makes the connection between studying the plumes of Europa and the atmospheres of planets around other stars.
What I would like to see is the definition of a habitable zone expanded. We don't want to keep thinking too narrowed about liquid on the surface, but broaden the scope and really try to embrace other worlds that might seem too far from the host star and frozen out when they really aren't frozen at all. At great depths, they harbor a warm, hydrothermal-driven, liquid water environment.